Okay, so the work number 6, carbon is burnt with air in a furnace with 150% theoretical air at a constant pressure of 1 atmosphere, and both reactants are supplied at 298 Kelvin. So what is the adiabatic flame temperature? So till the previous example we saw the heat calculations. Now let us try to calculate the adiabatic flame temperature. Okay. So carbon is burned with air with 150% theoretical air, constant pressure of 1 atmosphere. So initially the reactants are at 298 Kelvin, and what is the adiabatic flame temperature? Okay. The reaction is C plus 1.5. So for one atom, C atom, you need say 1 O2 molecule, but here since 150% theoretical, you are supplying 1.5 times the 1.5 kilomoles of oxygen. So 1.5 O2 plus 3.76 N2, that is air, giving CO2. Complete combustion takes place, and the excess air comes out, and this 5.64 N2 remains, okay, in the product, forms in the product. Okay, now from the first law you know that for the constant, this is a constant pressure process. So the heat interaction is nothing but the enthalpy change. The final state enthalpy is Hp and the initial state enthalpy is Hr. So now Hr is also 0 because CO2 and N2 all are basic elements and they are 298 Kelvin. So Hf is equal to 0, so Hr equal to 0. Okay. Now what is Hp? Hp is at a particular temperature you should get this. So let us assume that the temperature, adiabatic flame temperature is TAD. We will anyway, we have to assume the value for that. So 1 mole of CO2, so HCO2 at the calculated at TAD plus 0.5 of 0.5 kilomoles of HO2 calculated at the same temperature plus 5.64 HN2 at this. Okay. So now I can write this in splitting into two, like the formation and the sensible parts. So HF of CO2 plus delta HCO2 calculated at TAD plus 0.5, HF is 0 for O2. So delta HO2 at TAD plus 5.64 times delta HN2 at TAD. Okay. Now since Hp minus Hr equal to 0, since Hr equal to 0, Hp also should be equal to 0. So using that, I can rewrite this as delta Hs I put in one side, and HF of CO2 I take to the other side. So I get this equation. So now only by referring to the tables, so assume a temperature TAD, okay, go to the corresponding tables of CO2, O2 and N2, retrieve the value of delta H at that particular temperature, substitute that in the left hand side and see whether it is equal to the right hand side. So that is what the exercise we are going to do iteratively. So this is the equation I have. So let us assume the adiabatic temperature to be 1800. Why I am assuming lower temperature is because here you can see that it is 150% theoretical. When you put more air, you will see naturally that there is excess oxygen and more amount of N2 which is there. So this is going to reduce the temperature. So I initially take a temperature of 1800, try to evaluate, so go to the tables and get the value of delta HCO2 at 1800, delta HO2 at 1800 and delta HN2 at 1800, which are these three. Substitute this and get the value of this left hand side, and you see that the left hand side is now lesser than the right hand side. Okay. Now since it is lesser, I now increase my temperature, gas temperature to 1900, okay, and again retrieve the value of delta HCO2 at 1900, delta HO2 at 1900 and delta HN2 at 1900. These three are the values. When I substitute, I get now overshoot the value. Now I get a value which is greater than what is value required. Now this means that the adiabatic flame temperature should be in between these two. We just interpolate this linear way, assume that linearly in between these two. Okay, so no problem. So assume a linear interpolation like this: TAD minus 1800 divided by 1800 minus 1800 will be equal to the value of TAD is this minus the value at 1800 is this divided by the corresponding values at the 1800 and 1800 Kelvin. So you get TAD as 1843 Kelvin. Okay, so it's a simple answer. So why we have not considered dissociation here? Yeah, that's the assumption we are making. So for example, at 1800 Kelvin, some small amount of CO2 may dissociate, small amount, but it is not so high. So actually we can see that when the temperature is say around 1900 Kelvin, 1% of CO2 dissociates at atmospheric pressure, approximately 1% of CO2 only dissociates at 1900 Kelvin. So since the theoretical air supply is very high and the temperature we estimate to be within this less than 1900, it is better we didn't assume any dissociation. So if you want to really calculate accurately, you have to assume dissociation of CO2 also. That means you have to write the equation, this equation here, you have to write including the dissociation, like we can write this as C plus 1.5 O2 plus 3.76 N2 giving A times CO plus B times CO2 plus C times O2 plus 1.5 into 3.76 N2. So now for this carbon balance and oxygen balance will give you two equations, and one more equation you will get by considering this dissociation. Okay, so we can solve like this. You can attempt solving this problem like this, but you will not see much change in the temperature. So that is what, because of the excess oxygen here. So now you can see that if you consider small amount of CO may be produced at this temperature. So again you have to, now for this, if you want to solve this like this, you have to assume a temperature and calculate the equilibrium constant for this equation Kp, and calculate this ABC, you have to calculate as mole fraction, right, in the mole fraction terms, and calculate that, and calculate the Hp, and see, do this iteration, Hp is equal to HR or not, then you have to finalize the temperature iteratively. Okay, next problem, a insulated rigid 0.7 meter cube tank contains 0.05 kg of ethane and 100% theoretical air at 25 degrees centigrade, that is 290 Kelvin. Fuel is ignited and complete combustion occurs. Okay, now what is the final temperature? Okay, they are given this also, final temperature is between 2800 Kelvin and 3000 Kelvin. Now to make our life easier, without considering dissociation of the products, okay, then you have to find the initial pressure and final pressure also. So that is the equation here. So ethane C2H6 plus 100% theoretical air, so just use 2 plus 6 by 4, so that will be this 3.5 times O2 plus 3.76 times N2 giving CO2 2 CO2 3 H2O plus 13.16 N2. Okay, now for constant volume process, U react equal to U product, because it is adiabatic, correct. So we need actually calculate the final temperature. Insulated vessel, so Q1 to 2 equal to 0, adiabatic, insulated vessel, so adiabatic. So you get the first law when you apply to this, U reactant will be equal to U products. Now H reactant minus sigma NR RU and Ti will be equal to H product minus NP RU TAD. So this is the, so this is adiabatic flame temperature or final temperature I am assuming as adiabatic flame temperature. Okay, so now you calculate the equation like this. So sigma I am putting here because I am considering each and every species here. So 1 for the C2H2 you have 84667 into 84667 is the HF of C2H2 minus 1 into 8.314 into 298. So that is for this, plus 3.5 times O2, O2 HF is 0, but 3.5, 8.314 into 298 will be there, plus again nitrogen 13.16, 3.5 into 3.76 into HF is 0, but 8.314 into 298 remains. So, this will be the U reactant, the internal energy of the reactants. Now, internal energy of the products is now 2 times CO2. So, this is HF of CO2. Okay, then adiabatic flame temperature we do not know, but you just write the equation enthalpy, sensible enthalpy of CO2 calculated at TAD, which we are going to assume. Similarly, 2 is there here. So, RU times TAD also appears here. Okay. Similarly, for 3 times H2O, enthalpy of formation delta H at TAD and RU times TAD. Similarly, for nitrogen, there is no HF, straight away sensible enthalpy and of nitrogen TAD and RU into TAD. So, this should be equal to this. So, rearrange the equation to get write all the sensible enthalpies 2 times sensible enthalpy of CO2 at TAD, 3 times sensible enthalpy of H2 at TAD plus 13.16 times sensible enthalpy of N2 at TAD minus the number of moles of products into RU into TAD will be equal to, so whatever be the constant I am taken to right hand side and added to this. So, this will be the equation I get. So, once you assume TAD, I can substitute in the left hand side, retrieve the values of delta H's from the tables and fill up the calculated left hand side, compare with the right hand side. So, they have given that the temperature is in between 2800 Kelvin and 2900 Kelvin. So, starting with 2800 Kelvin, I see that the left hand side is less than the right hand side. But for 2900 Kelvin, I see the other way, right hand side is less than the left hand side now. So, interpolating again what we did in the previous case, I get the adiabatic flame temperature as 2890.5 Kelvin. Okay. So, as they have given, this is in between these two. Okay. Now, final temperature is got. So, what is the initial pressure? So, now they have given some data on the mass of fuel as 0.05 kg. Okay. For stoichiometric mixture, because it is talking about 100% theoretical air, so 3.5 number of moles of air into 4.76 into molecular weight of air divided by the molecular weight of fuel. So, that will be 16 kg per kg of fuel. So, mass of air in the container will be what? This is if 1 kg of fuel is present, then 16 kgs of oxygen will be present or air will be present. Now, you have only 0.05 kg of fuel in the vessel, that means 16 into 0.05, that is 0.8 kg of air will be present in the vessel. Okay. So, number of moles of reactant will be now the mass of the fuel divided by its molecular weight. So, C2H6 molecular weight plus mass of the air into divided by its molecular weight. So, this will be kilomoles. Now, you use the equation of state, ideal equation of state P1, which you do not know, into V 0.7 meter cube is equal to number of moles of reactant into universal gas constant into 298. So, we give the P1. Okay. It is about 100 kilopascals, 104 kilopascals. Now, products, number of moles of products is 18.16 kilomole, number of kilomoles of products. Now, for 0.05 by 30 kilomole of fuel, it is not 1 kilomole of fuel has not burnt. Since mass is given, mass of the fuel is given as 0.05 kgs. So, corresponding to that will be 0.05 by 30 kilomole of fuel. So, when 1 kilomole of fuel burns, you get 18.16 kilomoles of products. But now how much kilomoles of fuel is burning? 0.05 by 30 kilomole of fuel is burning. Corresponding to that, that number of product moles will be this 0.030267 kilomoles. Now use this in the equation of state. P2 into 0.7 is equal to 0.030267 into RU into T adiabatic. Now you get the pressure here. So you get about 10 times pressure rise approximately you get. Okay. So this is the constant vessel, constant volume combustion, where the temperature rises and pressure also rises tremendously. Now the next example is, consider the reaction CO2 giving CO plus half O2 at 100 atmosphere. The mole fraction of CO is given as 0.0289 mole fraction of CO and at 100 atmosphere pressure. Okay, what is Kp? So now you have to use the definition of Kp. So again the same thing what we have already seen. Alpha moles of CO2 dissociate, so that the mixture will have 1 minus alpha CO2, alpha moles of CO and alpha by 2 moles of O2. Now the mole fraction of CO is given as this. That means alpha by 1 plus alpha by 2. The total number of moles will be 1 plus alpha plus 1 minus alpha plus alpha by 2. This is equal to 1 plus alpha by 2. So that will be the total number of moles. Okay. Now alpha by 1 plus alpha by 2 is the mole fraction of CO, which is equal to 0.0 this. So from that you can calculate alpha. Now once you know the alpha, define Kp in terms of partial pressures. So the product x CO into x O2 power 0.5 divided by x CO2 into P by P naught. Now P is 100 atmosphere, P by P naught power 0.5. So now P by P naught is 100. So substitute for this. Okay, you know, once you know alpha is got, you can find all other number of moles and mole fractions, calculate that and find this. So Kp value is this. Okay, so this it's a slight demonstration. Once you know the one of the component, you can find the Kp directly when the pressure is given. So that is what is this. But it's not easy to calculate the temperature from this. Okay. Okay, the next problem is combustion. Consider the combustion products of decane with air. Equivalence ratio is 1.25. So rich combustion. Pressure is 1 atmosphere. Temperature is 2200 Kelvin. Okay. Now estimate the mixture composition, assuming H2O, CO, CO2 and H2 in the products apart from nitrogen. Okay. So that means I write the equation as C10H22 plus A times O2 plus 3.76 N2 giving B times CO, C times CO2, D times H2O and E times H2, and N2 is whatever coming from the auxiliary side, 3.76 times A times N2. That's it. Okay. Now this is the equation, and the equivalence ratio is given as 1.25. So the value of A is nothing but what A is 10 plus 22 by 4 divided by 1.25. So that is 12.4. So that you can get. So now carbon balance will give rise to one equation, B plus C equal to 10. So the right hand side B and C corresponding to CO and CO2 will be in the left hand side 10. H balance D here H2 plus E will be given is 22 by 2, 11. Okay. So then O balance will give you equation 24.8 here will be equal to B plus 2C here, 2C and D. So in the right hand side here it will be since you know the value of A, so 12.4 into 2, 24.8. So you know that. So that will be the O balance. So you get 3 equations, but there are 5 unknowns. No, 4 unknowns, because A is also known now. So only 4 unknowns, B, C, D, E. 4 unknowns are there, only 3 equations are there. So you need only one more equations. So 3 equations are got, 4 unknowns are there. So you need to generate one equation. Okay, now since the species involved are H2O, CO, this. See, we can discard N2, no, N2 is not, even if it is a product, it's okay, but we have to construct equations with the unknown number of moles, which correspond to the species of CO, CO2, H2O and H2. So one more equation is required. So we cannot use, see, we can, if you explore the choice of using CO2 giving CO plus half O2, okay, and H2O giving H2 plus half O2, you can use these 2 equations, but you need only one equation. If I select say one equation like CO2 splitting into CO, then H2 will not appear at all. If you take this equation, CO will not appear at all. So, we have to take an equation in which both are present. So, that for that we use what is called water gas shift equation, which is this CO plus H2O giving CO2 plus H2. So, in for example, when CO is formed, to reform the CO you use steam, so that CO2 and H2 are formed. So, H2 can be got from that. So, this is called water gas shift reaction. So, if you use this reaction and find the Kp for this, okay, then you can write the Kp in terms of B, C, D, E, which are the 4 unknowns. So, apart from the 3 equations got from the atom balances, a 4th equation can be generated and that can be used. So, since temperature is known as 2200 Kelvin, we can calculate the Kp value here. Once the Kp is known, define Kp using the partial pressures or mole fractions like this, and get the Kp in terms of B, C, D, E. Okay. So, I am getting the Kp value like this. So, I know the Kp value in terms of number of moles of the CO, CO2, H2O and H2. So, that is what I have written here. Now, how to calculate Kp? It is one function of temperature only, use the Gibbs function change. Okay. So, that is what we are going to do next. So, the elementary reaction is this. So, delta G is got as G of CO2 at 2000, this is product side first, G of CO2 at 2200. So, you can also put the overhead bar. I have just for simplicity I have removed it, plus H2, G of H2 of 2200 minus the reactant side, G of CO of 2200 and minus of G of H2 of H2O of 2200. So, from the again you can go to the tables. Okay, please understand that the Stephen Turn's book lists what is called Gibbs free energy of formation. Okay, you can use that, that's not a problem. You can use any table. So, if you use this table, then you get the values corresponding to this. Say Turn's provides Gibbs okay. Turn's book provides Gibbs free energy of formation. So, in which actually he says H2 O2, see, similar to enthalpy formation for basic elements, how we set the values of enthalpy formation of basic elements as 0. Similarly, Gibbs free energy of formation is also set to 0. Okay, so let us follow the Turn's book for this particular examples. You can also use NIST tables and other things, but I do not think there will be any big change in the values. So, the Gibbs free energy at corresponding to 2200 Kelvin for CO2 is this minus 396346. For H2 is a basic element, so Gibbs energy formation is 0, and for CO it is minus 302576 at 2200. Similarly, for H2O it is minus 124030 this. Okay. You can also calculate as H minus Ts, that is also possible. Okay. So, when you calculate Gibbs function, you get this value and calculate the Kp based upon the expression exp of minus delta G by RUT. So, you get this value. So, Kp is known now, and the expression for Kp in terms of B, C, D, E is also known. So, now this is non-linear equation. So, this equation along with the atom balance equations we have to solve. Okay. Now, if you take the atom balance equations, we can reduce the equations and write the equation only in terms of B. See, for example, here see here B plus C equal to 10. So, C equal to 10 minus B you can write, correct? 10 minus B. Similarly, here now C you have written. So, in this equation if you substitute for this, then D can be written in terms of B. Once D is written in terms of B, E also can be written in terms of B. So, in these 3 equations we can write everything in here we can see that B, in terms of B you can write all the equations. C equal to 10 minus B, D equal to 4.8 plus B, E equal to 6.2 minus B. So now you substitute this in this. So retaining B, all other C, D, E you write in terms of this, then you get a quadratic equation in B like this. Okay. Now if you solve the quadratic equation, you will get B value as either 4.64 or 16.526. However, physically what is B? In this equation, what is B? B is number of moles of CO. Total number of moles of C is only, number of atoms of C is only 10. So together B plus C can only be 10. So B cannot be 16. So this is wrong. So the physically correct value of B should be 4.64. So that you take and write the equation. That's all. So that's what is asked. So in this we have used equilibrium to find the proper products at a given temperature. When temperature changes, these values will change. You can see that more amount of dissociation has taken place for both CO2 and also for a significant amount of hydrogen is present. So this is what you can also use additional equations. If you want to may basically have say OH or H etc. or O, you can add them and you have to use appropriate number of equilibrium equations and say Kp1, Kp2, Kp3 etc. can be used to solve that. So multiple equations also can be used to solve for a particular composition. So if you can use n number of product species and n number of equilibrium equations to solve them. Okay, this is the last example. Okay, the 10th example is the last one. Here we have a system in which 1 kilomole of CO2, 0.5 kilomole of O2, 0.5 kilomole of N2 are present. Okay. Now this is heated. Okay. When it is heated, then the mixture is formed at the equilibrium. So at the temperature of 3000 Kelvin and 1 atmosphere, equilibrium mixture is composed of CO2, CO, O2, N2 and also nitric oxide NO. What is the composition? Okay. Do you understand? So initially the vessel has CO2 1 kilomole, 0.5 kilomoles of O2 and 0.5 kilomoles of N2. Now due to heating, dissociation happens and N2 also dissociates, O2 also dissociates, so that finally you get NO, CO etc. in the product apart from what was present previously. So the reaction is written as CO2 plus half O2 plus half N2 giving A times CO, B times NO, C times CO2, D times O2 and E times N2. Okay, this is the equation I have. So this is I don't know anything in the right hand side now. Okay, because of NO formation, N2 also is not known now. So 3 equations are got from the balances. Again, as we previously did, so 3 balance C, O and N balances will give 3 equations. Okay, now again I reduce the number of constants using 3, but how many unknowns are there? 5 unknowns are there. So try to use these 3 balances and only arrive at 2 unknowns. So that is what I am trying to do. Only A and B are kept as unknown, others are written in terms of A and B itself. So CO2 plus 0.5 O2 plus 0.5 N2 reactant, we can forget about this. Now the product is A CO, B NO, then I am writing C in terms of A, 1 minus A CO and D in terms of A and B, so 0.5 times 1 plus A minus B. Similarly, N2 is written in terms of B because NO. Okay. So now only 2 unknowns are there. 2 unknowns are there. So you need, but we have already used the atom balances. So you cannot use the atom balance anymore. So 2 unknowns should be solved by using equilibrium equations. So the total number of moles comes out to be 4 plus A by 2. Just you have to use it for total number of moles later. So now 2 elementary equilibrium equations are going to be used for this. So what are they? Obviously this CO2 giving CO plus half O2 will be the first one. Then N2 plus O2 giving 2 NO or half N2 plus half O2 giving NO. That is the second equation we use. And let Kp1 be the equilibrium constant for the first equation and Kp2 be the equilibrium constant for the second equation, correct. Now based on the definition, okay, what is the based on number of moles and total number of moles, so mole fractions, please understand that this is occurring at 1 atmosphere pressure only, okay, but temperature is 3000 Kelvin. So you can write the first equation, this CO2 giving CO plus half O2, you also keep this in mind. So A CO and CO, then you have O2, correct, CO and O2. So A CO and O2 are in the product side. O2 is 0.5, 1 plus A minus B power 0.5, okay. So that divided by 1 minus A and this 4 plus A by 2. So total number of moles should be divided in each term. So for example, for XCO we write as A by total number of moles, so which is nothing but 4 plus A by 2, 4 plus A by 2, okay. So similarly for this O2 you can write XO2 as 0.5 times 1 plus A minus B divided by 4 plus A by 2. Okay. So when you substitute all the mole fractions here, you will get this expression, okay, that is equal to exponent of minus delta G by RUT. This is actually at a particular temperature. So now here T equal to 3000 Kelvin as per the problem, 3000 Kelvin. Okay. So I calculate delta G at 3000 Kelvin and get the value of this. So Kp is known. So once Kp is known, I form one equation, Kp1 equal to 0.3273 will be equal to this non-linear equation involving A and B. One equation I have got, non-linear equation involving A and B. Now go to the next equation, Kp2. Similarly for this equation you have to evaluate. So Kp2 is defined as B by 1 minus B times 1 plus A minus B whole power 0.5. That again is this. Again calculate for this equation. So product is GNO, so NO, so GNO of 3000 minus reactants 0.5 GO2 minus 0.5 N2. From give the terms tables, this is gives energy formation will be 0, so this is 0, so you get this value. Kp2 will be 0.1222, that will be equal to this equation. So you have formed now two non-linear equations involving A and B, and while solving this in two non-linear equations, you will get A value as 0.3745, B as 0.0675. Now I calculate C, D, E, etc. because they are dependent on A and B values, and you can write the mixture as this. So here you have seen using two equations, and please understand that since non-linear equations are involved, you cannot always solve this by hand. You have to use computer programs, especially when more number of equations are involved and more number of unknowns are there. Okay. So this is the equilibrium equation. So you can see some amount of NO is formed here, and CO is also good amount of CO is formed at the very high temperatures. So very high temperatures we cannot avoid formation of NO, etc. Okay. So this will be the equation. So corresponding to this equation I have given this. Okay. So this finishes the worked examples part 2. So we will continue with the next topic.